everyone, and welcome to lesson 32.4. Today's lesson starts on page 454 in your Springboard books. We will definitely be jumping around a little bit in this lesson. On page 454, what we see first is talking about graphing our complex numbers on a graph, and we choose the x-axis as a real graph, and the y-axis is going to be our imaginary axis. So when we start graphing these, what we're going to see is that when we graph, for instance, our first one here, that is 1. Since that's a positive 1, it's going to be right here, right? So that our graph here only goes, the tip of this goes to 1. Okay, so there's our first one. For part B, we have 2i. So when we talk about 2i, that one is going to be on the imaginary axis, and again, it's going to go 2 units. Next, we have a graph for part C that's 2, -1. So 2 units to the right, down 1 unit, there would be part C. And then last but not least, we have part D, which is -3, -2i. So 3 to the left and down 2, there would be our vector for part D. Okay. Now, from there, we also can represent our sums and our differences. So looking at each of these, if we are adding our complex numbers together, we add the real components together to get 1. We add the imaginary components together to get positive 3i, right, when we're adding z1 plus z2. So if we were graphing the originals, we would have -2, 4i represented here, and we would have 3, -1 represented as well from there. So we went to the right 3 and down 1. And so then our final answer here is the 1, 3i plus 3i that we have represented down below. We can also represent our differences as well. So z1 minus z2 would be -5, and then 4 minus -1 is actually plus 5i. And we've talked a lot about how then it kind of turns into that negated front. So we still would graph z1, -2 plus 4i. But then when we start graphing this other piece, it's really like we are graphing -3 plus I. So from there, we would go to the left 3, up 1 for that resulting vector of -5 plus 5i that we see. Okay. Now, as we move on to page 455, we see about talking again, adding the real to the real, and then adding imaginary to imaginary. So add real parts and imaginary parts. And then same thing with subtracting. You can also substitute in the subtraction. It works the same way. Now, as we move on, then there's some practice with some operations. But more importantly, we also talk about finding the absolute value of our complex numbers, or sometimes we call that the modulus of a complex number. And I like to think about this and is kind of similar to finding our magnitude of our vectors, right? Notice it's represented with those absolute value bars, and we find that z is going to be found, the absolute value of a plus bi, by finding the square root of a squared plus b squared. So again, we kind of see that information kind of relating back again to what we were talking about earlier with vectors in the beginning of activity 32. Now, even though we are using imaginary pieces, our complex numbers, that distance, it's still going to be a real number. So even though we're using the component, the b value from an imaginary, your answer for your absolute value is always a positive real number because we're dealing with distance. Okay. Now at the top of the next page, on page 456, you see the idea of an argument. Notice it's written as a theta measure. The argument, again, is an angle measure informed with our positive real axis, and again, kind of moving around the coordinates. So again, to find that reference angle, theta value, our reference angle, we're looking for tan inverse of b over a. Okay, tangent is our friend. Now, we know that based on this axis, right, obviously we have 0 degrees, 90 degrees, 180, 270. Our theta value would be a quadrant 1 value. It's our reference angle. In order to get the quadrant 2, quadrant 3, quadrant 4, we know it's 180 minus theta to get between 90 and 180, 180 plus that reference angle, or 360 minus the reference angle. So those rules are still going to apply. So if we see, for instance, with number 7, if we are looking for this graph, well, first of all, if we're just at positive 1, we are going, we're going on the real axis 1 unit out. So think about, oh, okay, well, my argument then has to be 0 degrees because I'm on the positive x-axis, right? That there's 0 degrees. My absolute value then of this, if I'm doing the square root of 1 squared plus 0 squared, I'm just going to end up with 1 as my argument. The next one, if we graph 2i, that is going on the positive y-axis, right, going up. So we know that our argument on this one is going to have to be 90 degrees since we went up. So the argument of 2i, let me write this a little nicer. Argument of 2i, 90 degrees, opposed to this time, we are going to be, when we look for the absolute value of 2i, we know it's, the square root of 2 squared plus 0 squared, which is just 2. Now, a little bit more complicated when we talk about one like 2 minus I. We're moving to the right 2 and down 1. So we're focusing towards the quadrant 4 type angle measurement here. So when we're looking for that argument of 2 minus I, we're looking for tan inverse of b over a. So negative 1 over 2, or in this case, we'll just say 1 over 2 to talk about the reference angle. And, tan inverse of 0.5, 1 over 2, is about 26.6 degrees. Now, we know that would be the quadrant 1 value. So we know that we need to subtract from 360 that value of 26.6, because then that's going to give us our true value for quadrant 4, which is 333.4. And then the absolute value of 2 minus I, this time we have a and b are 2 and 1, so 2 squared plus 1 squared is going to be the square root of 5. Last but not least, we have an example that is coming to the left, 3 down 2. So think quadrant 3 type value. So your argument of negative 3 minus 2i, tan inverse on this. Now again, I'm going to use positive 3 and positive 2 because that's going to give me my reference angle. And I know this is quadrant 3, however, so I need to make sure that I add 180 degrees so that it makes sense where this value actually ends up at quadrant 3 value, since we went to the left and down, so 213.7 degrees. And then absolute value of this, square root of 3 squared plus 2 squared is the square root of 13 on that one. Now, as we jump ahead and finish this out, we're actually going to skip a lot of things, skipping the next 2 pages here. We're actually going to jump to number 17, which is on page 459. And what we see here is we have some complex numbers involving these square roots here. And if we are looking for the arguments and the absolute values of each of these, the argument, what we're going to do is we are going to see, the absolute value of this square root of 2 square root 3 squared plus, again, parentheses are your friend, 2 squared would give us 4. And then we would do the same thing for w. This was, which is going to be 1 plus square root of 3i, or just calling that absolute value of w, square root of 1 squared plus square root of 3 squared. We end up actually getting 2. Okay. Now, what we notice is if we multiply these 2 vectors together, right? So 2 square root 3 plus 2i, and then 1 plus square root 3i. If we expand this out, double distribute, combine your like terms, all that fun stuff, we end up getting 8i. And what we notice on this one is if we find the argument here, it's just the square root of 8 squared, so we just get 8. What is the relationship between 4, 2, and 8? Well, something you're going to notice is if you multiply those values together, what you're going to see is that the individual absolute values multiplied together are going to equal the absolute value of these values multiplied, okay? Now for the arguments of these values, okay, the arguments, well, we would need, these are both quadrant 1 values, which is good information for us. So the first one, we're going to have 2 divided by 2 square root 3. So it's 60 degrees, and then we're going to have tan inverse of square root 3 divided by 1, which is, one should have been 30 degrees. So what we see on this one for z, it should have been 30 degrees. This might be a good time to show that the complex numbers here, we can also, if you go into the math menu of complex, if we look for the angle, and I'm going to type this in just to double check my work where I went wrong. I have 2 square root 3 plus 2 30 degrees. That's what I said. What did I? Oh, sorry. So it should have been 30 as the angle measure there, and then same thing would have been 60 for the other. So what we see, order of operations. Oh my gosh, that's where I went wrong. 2 square root 3 needed the parentheses, so that's where it was 30. So 30 degrees then on that. So we have 30, we have 60. And then when we multiply, what we would see the argument on that one using 8i, and again, math menu, scroll over to complex, and then option 4 is the angle measure. If we do 8i, we see that our argument is 90 degrees. So this time, what's the relationship between 30, 60, and then 90? Well, on this one, what we're seeing is that if you add the arguments together, you get the argument of the multiple. So you're adding them then to get the multiples. Okay, so both of those are really important formulas to know. Okay, and we can test this out on some of the other examples that they are giving us. For instance, one like letter C. Okay, and again, practice using the calculator on this one. If we do the math menu, we can check out the two individual absolute values and arguments. So we have 1 plus I. We see we get 1.41. If we test out then the absolute value of then 2 plus 2I, we see we get 2.82. And if we were to test out then the absolute value of those multiplied together, so parentheses 1 plus I times 2 plus 2I, you get these two values multiplied together, or approximately that, since we're dealing with decimals. That again, if we use these exact values, we would have those. Okay, we see that in action on that, and then it would be the same thing with the arguments. We could see that they would be added together. All right. So that is all we have then finally for the end of lesson 32.4. Make sure you have these two formulas down and we'll work more with them in class.